Okay, so in the previous video, we studied the first law of thermodynamics, and what it says is that the change in the total energy of the system, which is E thermal, is equal to the work either done or being done by the system and the heat that is being added or removed from the system. So if the work is positive, right, that means you're compressing the system, you're doing work on the system, so the thermal energy increases. If the work is negative, that means the system is doing work, it's pushing something, therefore this is negative. If Q is positive, that means you're adding heat, you're heating the system, you're adding heat to the system. And if Q is negative, you're cooling down the system, you're removing energy through heat from the system. So this is all summarized in this beautiful equation, which is known as the first law of thermodynamics, right? And it's nothing else but conservation of energy, right? So let's look at this simple example. We have a process, a system that goes from this initial state to the final state. And there's three ways in which the system can go by doing process A, process B, and process C. These are three different expansions. So the question is, for which process is the heat transfer the largest? Well, the answer is process A. In all these cases, the work being done is negative. The system is losing energy because the system is expanding. But also, the change in energy, delta E thermal, is the same for the three processes because the change in total energy only depends on the final and initial states. It doesn't depend on how you go from one state to the other. So delta E is the same for all three. So this has the smallest work. So this loses the smallest amount of energy through work, and this process A has the largest work, right? So the process A is losing the more energy through work. So therefore, A is the most negative, right? So Q have to be the most positive to so that you get the same delta E for the three processes. There are three processes that, for in the case of the ideal gas, that we would like to understand, and we would like to understand the energy balance for these three processes: isochoric process, isothermal process, and adiabatic process. So what I'm going to do is show you a small simulation for these three processes, and as I do that, I'm going to be filling out this table here. I have for the isochoric process. So for the isochoric process, I'm going to see what happens to delta E thermal, the work and the heat. Same for the adiabatic process and same for the isothermal process. To do that, I'm going to use this simulation, which shows an ideal gas here, and this is a piston here. And if you compress the gas, you're doing work on the gas, so the total energy would increase. If the gas expands, then the work is negative and the energy would decrease. And same for and here this shows the heat that is going in and out. If the arrow points this way, it means heat is going into the system. If the arrow points the other way, that means heat is going out of the system. So let's start with an isochoric process and let's increase the energy. Let's see what happens if there is a positive change in energy for an isochoric process. So let's start with a pressure of, let's say, 3, and let's finish with a pressure of 9, and the volume remains the same. So let's see what happens in that case. And that is your system. The volume is not changing. Work is not done on the system, or the system is not doing work. There is no work because the volume is not changing. So this is 0. That's an isochoric process. And Q, all the energy, the 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 energy change is just Q. So all this heat that goes into the system goes into the thermal energy of the system. So this is positive. Now let's see what happens for the inverse process where you start at 9 and finish at 3, right? So this is the other process. So here we're going to be cooling down. So and you can see now heat is going out of the system and the energy is decreasing. So the energy is negative and heat just went, there's no work because the volume didn't change and heat went out of the system. So this is the energy balance, the first law for an isochoric process. Let's look at an adiabatic process. An adiabatic process is one in which there's no heat going in or out of the system. So then we have 0 and 0 here. And let's see what happens for an adiabatic process. And let's start with a volume of 3. Let's do an expansion, a volume of 3, and finish with a volume of 9. And let's see what happens here. So this is your adiabatic process. The system is expanding, so it's doing work. As it does work, right, this much work, the energy decreases, right? So this is the work that the system does. This is the energy that the system loses. So therefore work in this equation here, work is negative and the change in energy is negative. Uh, so now let's look at the other process in which we have an adiabatic process and we go from 9 to 3. So this is a compression, right? The system is going to be compressed. Somebody's going to be doing work on the system, but there's no heat going in or out the system, so we can do this. And you can see now the energy increases. So the energy increases. So this here is plus, and this is plus. So whatever work was done into the system all goes to the thermal energy. Finally, let's look at an isothermal system. An isothermal has this property, the energy doesn't change. The energy doesn't change. So the energy of the system remains constant. So let's start with this pressure. Let's see a volume of, let's start with an isothermal compression. We start with 9 and finish with 3. That is an isothermal compression. So you're adding energy to the system by doing work, but at the same time that energy is flowing out of the system as heat, right? So that whatever energy you add to the system by compressing the system is going to go out but as heat. So therefore, in here, you have that you've done work on the system, you add energy through work, but you lose that energy uh, as heat. So these two cancel each other. These two cancel each other, and the thermal energy is 0. And now we can look at the isothermal expansion. And the isothermal expansion is the opposite process. Now the system expands, and we can calculate this. And then you can see this is it got 3, 9. That is your isothermal expansion. Now the system is expanding, is pushing something, so the work is negative. And so to do that, to be able to expand and do work, then you have to add energy to the system as heat, and you use that energy to push. So the heat is positive. In the video, there is a detail. In this simulation, there is a detail that the actual uh, equation he's using is delta E thermal is equal to Q minus W. It's just a convention here. He's using, the person who wrote this simulation is using this convention for the heat. In the book, we'll use this convention, heat being positive. If you do work on the system, you increase the energy, and if you if the system does work, this is negative and the energy decreases. All right. Thank you very